A very good morning or evening to my IEEE fellowships, and my name is Philip Tan Boon Hong, and my course is 3E with the student ID of 100160 and graduated from Utah January 2020 trimester with the e-convocation held in August 2020. Today I would like to present on the title of Compact Planar Antenna for Metal-mountable UHF RFID tech design, which was finished and conducted in Utah January 2020 trimester. So this is the overall outline of the video, the brief summary of what I'm doing in my RFID project. So it consists of a introduction, the general introduction on what is RFID and its system, what are the aims and objectives to do this project, what are the contribution of this project once it is done, and how is it contributed to the society, the methodology and the overall work plan, the procedure on how this project is being conducted, the result and the discussion of the proposed tech, so that we want to analyze and see what kind of performance of this RFID tech has, and the conclusion of the overall project, as well as the recommendation for the future work, so that the disadvantage of this project can be amended and to be done in future to be amended away the disadvantages. So first of all, what is radio frequency identification, RFID? So RFID make use of the signal electromagnetic wave to automatically identify and track text attached to the object. So once this is done, is that the tag itself contains electronically stored information, so we can know that what kind of object is being mounted on. So the tag attached to that object, we can identify what kind of object is it. So how does the tag is being activated? It is being activated once the reader antenna has reached one value known as the threshold value. So once the tag antenna is activated, it will backscatter back the information back to the reader antenna through free space in the form of signal, and then the reader antenna will send the signal to the reader through RF cable, and then the reader will decode what kind of information is it, and then the information will display inside this computer. So this is the overall system of the RFID system which I've described just now. So what are the aim and objective of this project? So first of all, I would like to select a tag antenna structure which is able to provide quasi-isotropic radiation pattern in a considerably good range when it is mounted on the substrate. What does it mean by considerably good range? Which means that the read distance must more than 5 meters, as well as the quasi-isotropic radiation pattern is a pattern that it is near to omnidirectional pattern, which the orientation between the tag antenna and the reader antenna doesn't really that matter. Any orientation, the tag antenna is still able to detect the signal from the reader antenna and activate the tag. So secondly, since I would like to make my tag antenna size to be very small, I would like to employ some miniaturization technique to make it very complex. So once the tag antenna size is very small, there are some jeopardization because of the RF performance will be affected once it become very small. So there are some tuning and impedance matching has to be done, so that the small antenna size is still able to achieve impedance matching between the tag and the microchip at that UHF resonant frequency, which is in 950 MHz in Malaysia RFID range. So what are the methodology and work plan of the project? So this is the software I'm using to optimize my RFID, the parameters to optimize so that it will be resonated at 915 MHz, as well as it is very small. So what are the foundation of CST Microwave Studio software? So this software make use of the finite integration method. So in a layman term, it is by modeling a 3D diagram in such a form that you can see and zoom inside, and you can see it is just a square cube. So this software solves the Maxwell equation in this small square cube and add up everything together to model this 3D equation, so that the overall field equation or the Maxwell equation can be done in this simple method instead of solving this complicated 3D model. So this method to model this is very accurate and so that it is very accurate and near to 100%. The approximation is very accurate. So this is the measurement being done inside the anechoic chamber. So once the tag is optimized, we would like to fabricate it, and then the measurement will be carried out inside this anechoic chamber. So the overall system is using the Voyantic tag formants. So that system is very mature in industry to test the RFID, UHF RFID tag performance. So the anechoic chamber is used to make sure the external interference is minimized, as well as the distance between the reader antenna and the tag antenna must be a quarter wavelength separated, so that the far field radiation pattern is achieved. It's not in the near field range. So to measure the radiation pattern in the YZ plane, we would like to rotate it around the x-axis. To measure the radiation pattern in the XZ plane, we will rotate around the y-axis. To measure the radiation pattern at the XY plane, we rotate around the z-axis. The reader antenna will stay in a fixed location, just that the tag antenna is rotating. Why we want to measure these three planes? Because we cannot measure the exact 3D radiation pattern. Instead, we measure this three plane pattern to approximate a 3D radiation pattern. So this is the description which I've already mentioned just now. So how does the radiation pattern being converted into the read distance radiation pattern? So it's being converted using this equation. So it depends on the wavelength. The PTX is the transmitter power of the reader antenna. The GTX is the gain of the reader antenna. The GR is the realized gain of the tag antenna. And the PC-on is the chip sensitivity, which is the minimum power required in order to turn on the tag antenna. So it is being converted into this equation to get the 3D radiation read distance pattern. So this is my overall proposed UHF RFID tag. So it consists the inlay before we wrap it. This is the thing. So it consists of two ground planes. So the white color part is the substrate. The gray color part is the copper part. So this is the square split link resonator, and then this is the extended strip line. So the radiating patch is actually this outer part. And then the extended strip line is provide the purpose of capacitive coupling within the mindered T-mesh loop in order to excite this outer part of the radiated patch. And then the mindered T-mesh loop, the pair of notches, the inductive stub is used for impedance matching, fine frequency tuning, and miniaturization technique of the tag antenna. And then the chip is embedded inside this narrow square gap. So the overall size we can see from here is 28 times 28 times 3.293 in mm, and in terms of wavelength is this. So it's being proven is very compact for my RFID tag antenna design. So these are the overall parameters which I'm using to optimize by using CST Microwave Studio software, so that it will be resonated at 9.5 MHz, and then the matching is very good at that frequency. So this is the inlay. Before we fabricated it, we would like to design this inlay in CST Microwave Studio, so that the fabrication process we can print this pattern inside the substrate, so that the unwanted part can be etched away, so that the desired copper part can be designed and such pattern will obtain. So this is the part I've obtained from this is the RFID tag antenna structure for my design. And then so this is from the top view, and this is from the side view. So from the top view, the white color part is the substrate, and then the gray color part is the copper part, and then the line part is the PET. So from here I'm using the PET double-sided substrate. So the double-sided is actually a copper part. So we etch away the unwanted copper part so that this structure is able to obtain. So we can see from here, so we can see the substrate is being shown here, and then the copper part is being shown here. And then after this pattern is done, so we wrap it around inside a Duroid 6010 substrate. So the specification of the Duroid 6010 substrate is shown here. With the die, one of the key point to mention here is the dielectric constant is 10. So the higher, one of the design miniaturization technique is that the higher the dielectric constant, the possible is it to shrink down the tech antenna size to become smaller. But one of the jeopardization is that the RF performance will reduce. So this is also one of the disadvantage of it by having high dielectric constant. So the chip I'm using is the Monza 5, which is manufactured by Inbinji, having the impedance of this amount, 14.56 minus J 161.25 ohm at 1950 MHz, and with the read and write sensitivities as shown here. So we can, one of the keynote we can see from here, the write sensitivity is quite low. So the lower the write sensitivity, the lower the power itself to activate the tag, so which translated into the read distance is much more longer. So after I done the optimization, so I simulated it and see I get the data from the software. So we can see from here the matching is very good, minus 22 dB, which convert to the power transmission coefficient. 90% of the power is being transfer from the tag to the chip, so it's very good, the matching. So as we can see from here, this is the overall radiation pattern we get. So we can see from here the quasi-isotropic radiation pattern is obtained. So from the H plane we can see is near to a figure of O, from the E plane is near to a figure of 8. I cannot get the perfect figure of O and the figure of 8 is because my RFID tag antenna is not designed in half wavelength. From antenna theory, we know that the optimum performance for the dipole antenna is half wavelength, right? So, but for RFID tag antenna, half wavelength is way too electrically large, so it's not so suitable for RFID, because in your UHF range, we would like to make the antenna size too small. We don't want to make it so big, so we optimize at the 915 MHz. So this is the radiation pattern near the half wavelength is also able to obtain, which proves that the performance is quite good. So one of the main disadvantages of my RFID tag is that I cannot mount it on a metal, because we can see from here when we mount it on the metal, the resonance frequency is shifted to near 925 MHz, about 100 MHz, about 10 MHz is shifted. So and then the radiation pattern is no longer in quasi-isotropic radiation pattern. You can see from here, half of it becomes a ball side radiation pattern. So the objective is not met when it is mounted on the metal. So the overall conclusion of my RFID project is that all the objectives are met, stated just now. And then, as I already mentioned, 90% of the power is transmitted. And then the realized gain of minus 5 dB when it convert to the read distance using the formula just now I've already mentioned, near to 9.2 meter is greater than 5 meter. So the objective is achieved. And then the resonance frequency and the realized gain of the proposed antenna is very stable as long as it is mounted on any substrate material, which means that any size or any thickness of it, as long as it is the substrate material, the resonance frequency and the realized gain will not deviate much. So this is also very good as long as it is mounted on a substrate material. So what are the disadvantages and should be amended if possible for my RFID tag project is that aluminium conductive material should be used instead of copper. And also, as I already mentioned just now, high dielectric constant substrate will jeopardize the RF performance of the RFID tag antenna performance. So low dielectric constant should be used instead of high dielectric constant. So as well as the lower the dielectric constant substrate, the cheaper it is. So it's better to low dielectric constant substrate if possible. And then for copper is used instead of aluminium if possible, but copper itself will also jeopardize a bit of the RF performance, but it is much cheaper. And then so as well as the tag antenna structure is able to provide quasi-triidral. This is one of the main research should be done in near future, is that the RFID tag antenna structure should be investigated so that when it is mounted on both substrate and also metal, the quasi-isotropic radiation pattern is achieved, provided the radiation pattern and the desired resonant frequency at the UHF range is able to provide such radiation pattern, quasi-isotropic radiation pattern. So why we would like to do that in near future if possible is because of we know that nowadays the technology is getting more and more advanced. So if this kind of RFID tag structure is able to investigate and able to manufacture it, it is very convenient to any kind of application for that RFID tag antenna. So this is the overall of my video. Thank you.